So hello and welcome back to lecture 9-2 in class activity 2. We're going to use frequency response design to create a lag compensator for a control system with the following open loop transfer function that will have a static error constant kV equal 10 and a phase margin of 50 degrees. So the open loop transfer function is K over S times S plus 5 squared, where kV, the velocity error constant, is defined to be the limit as S goes to 0 of S times Kg of S H of S, and we set that equal to 10. So we're going to have K over 25 equals 10. And when we solve for K is equal to 250. So for step 2, what you're going to do is go to MATLAB and generate the Bode plot for the open loop transfer function with a gain of K equals 10. So on the left here, you will see that I have done this, and that this Bode plot has a phase margin of 0 degrees and a gain margin of 0 decibels at 5 radians per second. That means that this system is exactly marginally stable. Remember, relative stability means you'd want the phase margin to be a positive number, ideally between 30 and 60 degrees, and the gain margin to be a positive number, ideally 6 decibels or greater. But 0 degrees, 0 decibels is marginally stable. Negative gain margin is unstable. Negative phase margin is unstable. So for step 3, we're going to find the phase margin, the gain crossover frequency, etc. If you get these in MATLAB, you don't have to actually do this by hand. You do need to be able to do this by hand on your exam though. But since I've generated this in MATLAB, I have given you that information. You actually don't use it for a lag compensator. You do use it for a lead compensator, but on to step 4. So now we're going to find phi sub m, which is defined to be the value of the desired phase margin minus 180 plus a 10-degree fudge factor. That number is arbitrary. It could be 5 or 10, but it's just something so that you can compensate for the attenuation that's going to happen when you add the lag compensator. So that phase margin 50 minus 180 plus 10 is going to equal negative 120 degrees. Now, for step 5, you're going to go to the Bode plot that you generated in step 2, and you're going to search the Bode plot to find the frequency where the phase is negative 120 degrees. So we're going to do that now. And when you search the Bode plot, and this can be an approximation, I actually did it in MATLAB, so I know exactly where it is. What you're going to find is that omega sub f is equal to 1.34 radians per second. For step 6, we are going to find beta, where beta is defined to be 1 minus sine phi m divided by 1 plus sine phi m. So we found phi m was negative 120 degrees in step 4. So we're going to have beta equals 1 minus the sine of 120 degrees divided by 1 plus the sine of 120 degrees, which is going to equal 13.93. Your question may be, what exactly is beta and why do I care about that? Well, beta is an attenuation factor that relates Z lag and P lag in the compensator. So we use beta to help us define the values for the 0 and the pole for the lag compensator. Step 7, we're going to get that Z lag is equal to 0.1 times omega f. So similar to when we did the lead compensator, this omega f gives us a ballpark for where we want the center frequency to be for our lag compensator. It won't be exactly there, which you'll see when I plot the compensated Bode plot, but it will be in the ballpark. So Z lag is equal to 0.134 radians per second, which is 0.1 times omega f. And now P lag is Z lag divided by beta, that attenuation factor I talked about. So P lag is 0.0096. And then step 8 is to find the gain, Kc, for the compensator, which is 1 over beta to compensate for the attenuation from the lag compensator. So that is going to be 0.072. And then finally, we draw the transfer function for the compensator, which is Kc times S plus Z lag over S plus P lag, or 0.072 times S plus 0.134 divided by S plus 0.009621. So in the next step, I now have multiplied the compensator by my open loop transfer function. Using my gain Kc and my gain K, I have regenerated my Bode plot. So the first thing you should notice now is that since this is a lag compensator, there is now a dip in the magnitude and the phase plot. This dip represents where the lag compensator has now changed the phase margin, and we actually beat the spec of 50 degrees because it is actually 68.9 degrees, and omega F, or the center, is actually at 0.716 instead of 0.134. But the main thing to notice is that we were able to create a lag compensator that was going to meet our design specifications for the phase margin. So now if you come down, we have a unit ramp response, and the original system was marginally stable, so it did not track the ramp at all, which is that blue line. And then afterwards, we were able to use KV equals 20 to track the ramp.